For a second, imagine the biggest number you know. What is it, 100 or 1000 or 300 millions maybe? I don't know, but what if I told you that actually the largest number in mathematics is called a volt? That's right, a volt, but in Spanish, rayo. This number takes its name from its creator, Agustín Rayo, a Mexican philosopher who defined it during a competition in the MIT. But how big is Rayo's number? Get ready, because we're about to embark on a fascinating journey through math, starting with very simple concepts and venturing all the way to the limits of pure theory itself. First, we need to put other large numbers into perspective. Let's start with the googol, which is defined as 10 raised to the power of 100. A googol has this many digits. It seems enormous, but in reality, it's just the beginning. Take a googolplex, for example. 10 raised to the power of a googol. That's vastly larger, with this many digits. We could keep going, defining a googol duplex, a googol triplex, and so on. While this method clearly produces colossal numbers, we're still confined to exponential notation. And why do I say confined? Because mathematics extends far beyond mere exponentiation. Let's start with a simple visual way to understand recursive operations: polygons. Take 3 inside a triangle. What does it mean? Is this about geometry and big numbers? And not exactly, it's just a way to represent operations. Here, 3 inside a triangle means 3 raised to the power of 3. And more generally, n inside a triangle means n raised to n. Now, what if we have 3 inside 2 triangles? We solve it from the inside out. First, 3 inside one triangle is 27, then 27 inside a triangle means 27 raised to 27. An enormous number. The next step, a number inside a square. 3 inside a square means 3 inside 3 triangles. In general, n inside a square is n inside n triangles, so 3 inside a square becomes, first, 3 inside 3 triangles. If you solve the first triangle, you will get 27, then 27 inside a triangle, which is 27 raised to 27, and finally, that result inside another triangle. In other words, 27 raised to 27, all that raised to 27 raised to 27, which is absolutely enormous. To put this in perspective, 27 raised to 27 alone is already this huge number. And now we are raising that to itself. If we keep going with more geometric shapes, we can generate even more big numbers. But let's stop at 2 inside a pentagon, also known as mega. Not this mega, that mega. Here's how it works. 2 inside a pentagon means 2 inside 2 squares. 2 inside a square means 2 inside 2 triangles. If you solve the first triangle, you will get 4. Then the second triangle is 4 raised to 4, which is 256. Now, 256 inside a square means, by definition, 256 inside 256 triangles. If that seems incomprehensible, just try imagining a googol inside an octagon. It is beyond human intuition. Polygons are very intuitive, but they have their limits. There is a similar operation that also uses exponentiation towers, but it's not the same. If we restrict ourselves to natural numbers, you will agree that multiplication is essentially repeated addition. For example, 3 times 4 is just 3 plus 3 plus 3 plus 3. Similarly, exponentiation is repeated multiplication, so 2 raised to 3 means 2 times 2 times 2. Now we can define tetration. Just as exponentiation stacks multiplications, tetration stacks exponentials. For example, 3 tetrated to 4 means 3 raised to 3 raised to 3 raised to 3. But before we go further, let me clarify the notation. Instead of writing m raised to the power of m, we will use n up arrow m. Tetration then is represented with 2 arrows. So 3 2 arrows 4 means 3 arrow 3 arrow 3 arrow 3, which is the same as 3 raised to 3 raised to 3 raised to 3. In general, n titration m, or n two arrows m, is n arrow n arrow n arrow n repeated m times. But we can go even further. Pentation stacks titrations, meaning that m pentation m is n titration n titration n titration n titration n repeated m times. This quickly becomes extremely complex. For example, 2 pentation 3 breaks down as 2 titration 2 titration 2. Since 2 titration 2 is just 2 raised to 2, which is 4, we get 2 titration 4, which is 2 raised to 2 raised to 2 raised to 2. In other words, 2 raised to 16, or 65,536. Now, imagine adding just one more arrow. The numbers become so large that they are practically incomprehensible. For instance, 2 ℓ 3 is already so enormous that you couldn't write it out in the observable universe, not even if you filled an absurdly amount of observable universe with digits. And even that description is a gross understatement. The reality is actually far worse. This number dwarfs even 2 inside a pentagon. But how far can we really go with arrows? In 1971, Ronald Graham and Bruce Rothschild published a paper proving a theorem in Ramsey theory concerning certain edge colorings of hypercubes. Specifically, they show that while it's impossible to avoid a particular monochromatic structure beyond a certain dimension, the threshold dimension remains unknown. However, they established an upper bound for this dimension. Consider the following sequence: G0 equals 4. Very easy. Then G1 equals 3 ℓ 3. An already incomprehensible number. Then G2 is equal to 3 G1 arrows 3. And in general, Gn is equal to 3 Gn minus 1 arrows 3. This sequence is absurdly fast growing. Just its second term is too large to write out in the observable universe. Yet G2 is so colossal that G1 is practically negligible in comparison. And the gap between G3 and G2 is even more mind-bending than the one between G2 and G1, with each subsequent gap exploding even further. Well, Graham's number is defined as G64, a 3 followed by G63 arrows and another 3. And guess what? That upper bound is exactly what the theorem established for the hypercube's dimension. It's an unimaginably vast number. Any finite number compared to it may as well be 0, unless of course we're talking about G65 or larger. Now, if we can even begin to grasp the magnitude of the first few terms, what's the point of discussing G100 or G a Google? I'm not sure, but what do I know is an even more massive number, and its construction is actually simpler to understand than Graham's number. In math, there's a subject that studies trees. Not those trees, these trees. Graph theory, which deals with nodes and edges. Imagine a game where you build a forest using nodes of different colors, with 3 simple rules. First, you build the trees one by one, in order. Second, the nth tree can have at most n nodes. And third, no repeats. You can't build a tree that contains any previous tree as a subset. These rules are somewhat simplified, but they work for explanation purposes. Break any rule and your forest, well, goes up in flames. Now let's play. Suppose I give you one color, say red. How many trees can you build? Just one, not much of a forest, right? So let's add another color, green. Now, you may think the answer is 2, but if you arrange them cleverly, you can actually build 3 trees without breaking the rules. This leads us to define the tree of n function, which is the maximum number of trees you can build with n colors, where n is a natural number, of course. We already know that tree of 1 is just 1, that tree of 2 is 3, but here's where things get insane. If I give you 3 colors, how many trees can you build? 6, 10, 100? In fact, tree of 3 is unimaginably larger than Graham's number. Yes, tree of 3 dwarfs even G64, and not just by a little. Comparing it to a bigger Graham's number like G100 or G sub G sub G sub G64 doesn't help. It's unfathomably large, and that's just 3 colors. Now imagine 3 of a Google. It is beyond description. At the highest levels, mathematics stops being about numbers and instead becomes a world of abstract ideas and structures. In set theory, for example, you won't find theorems about calculus or limits. Instead, you will encounter statements like, every infinite subset of a countable set is also countable, or the set of all subsets of natural numbers is uncountable. These aren't about numbers, they are about definitions, structures, and logical relationships. But how does this connect to enormous numbers like Rajos number? All of modern mathematics is built on Zermelo-Frankel set theory with the axiom of choice, a formal system defined in a precise first-order language. This language has a small set of symbols, but with them we can express everything, from the number 0 to the most complex theorems. For example, 0, defined as the empty set, can be written in about 8 symbols. 1, the set that contains the empty set, takes around 20 symbols, and this axiom takes 21 symbols. This seems inefficient to write numbers, but it's the price of absolute rigor. In fact, proving something as simple as 1 plus 1 equals 2 in full formal detail takes hundreds of pages. Not because the proof itself is long, in fact it's just 2 lines, but because you must first define all the underlying concepts, like ordinals, addition, and those things, using only these basic symbols. Now, imagine a function that leverages this formal language to define unimaginably large numbers. Rajos function. Raj of n is defined as the smallest number bigger than any finite number that can be defined by a first-order set theory expression using at most n symbols. At first, this seems weak. Raj of 5 is 0, because you can't even define 0 in 5 symbols. Raj of 8 equals 1 because the largest definable number is 0, so Rajo adds 1, and Raj of 34 is equal to. Still struggling to define anything beyond 1. But here's the twist. Rajos function grows faster than any computable function. Once you feed it enough symbols, it explodes, past Graham's sequence, past 3 of n, and past every other named large number, because it harnessed the full power of set theory itself. And that's just the beginning. In 2020, it was proven that using a certain number of symbols, you can construct exponentiation towers. Later, this bound was improved, ultimately leading to this inequality. For example, Raj of 320 exceeds 16, while Raj of 380 surpasses this number, which has 20,000 digits. Yet, this still doesn't come close to G64. However, as you allow more symbols, you can encode increasingly powerful operations. At some point, say with 1,000 symbols, you could write 3 tetration 3, then 3 pentation 3, and eventually even G1. Continuing this way, you'd reach G2 and finally G64. I'm not certain of the exact threshold, but I'd estimate it requires fewer than 1,000,000 symbols. Now consider the scale of 3 of 3. Even if it took 100 million symbols to define, I'm sure it doesn't take that long. It wouldn't matter. We are manipulating the very foundations of definition itself. This brings us to Rajos number, defined as Raj of a Google. In other words, the smallest number bigger than any finite number definable in first-order set theory using at most a Google symbols. This is absurdly large, beyond computation, beyond imagination, and beyond math itself. There is no meaningful way to surpass it without reinventing the language of definition. Sure, Raj of a Googleplex is even bigger, but that's not the point. The point is, Rajos method is the most powerful way we have to define large numbers, because all math is expressed in this language. Those are the most colossal numbers we have ever defined. But what about infinity? Is there something even beyond it? That's exactly what we'll explore in the next video. If you enjoyed this video, don't forget to like and subscribe. See you in the next one.